Assalamualaikum and hi, my name is Muhammad Razim bin Mazlan. My metric number is DF230114. This is our group member. Okay, today I want to present about introduction. Landslides are the downward movement of soil, rock or debris triggered by natural factors like heavy rainfall, earthquakes, and volcanic activity or human activities such as construction and deforestation, water infiltration weaken soil. Increasing the risk of landslides, they can cause significant damage to infrastructure, agriculture, and ecosystems, as well as pose a threat to human life. Preventing landslides requires careful analysis and mitigation of risk factors. Thank you. For our case study, we choose Havilian landslide at Pakistan, which occurred from November 21st to 23rd, 2015, near Pona village in Abbottabad, was triggered by tension cracks from an earlier earthquake and heavy rainfall. The disaster blocked the Havilian Sajikot Satora road, destroyed 12 houses, and isolate over 25 villages with 4.16 million cubic meters of material displaced. The event highlighted the region's vulnerability due to steep slopes, weak soils, and seismic activity, emphasizing the need for improved soil management and geological risk mitigation to prevent future landslides. Thank you.
Assalamualaikum. I will continue about the objective of the project. First objective is slope failure causes, geological slope geology and tectonic activity, hydrological rainfall induced soil saturation and increased pore water pressure, seismic influence of earthquake and mild tremor. The second objective is impact of soil saturation and stability. Soil saturation reduce shear resistance, increase pore water pressure triggers slope collapse. Direct shear test used to analyze stability. The third objective is effectiveness and sand replacement method. Studies soil behavior under varying compaction level, assesses relevance for improving slope stability in the Havilian region. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Al-Qudri bin Baharom, Novometric DF220071, and today I will be present about problem statement. To understanding landslide Havilian case study, the objective is to investigate the role of saturation and pore water pressure in slope collapse using direct shear test. Advanced understanding of landslide mechanics for improved risk management and mitigation techniques. The key finding is rainfall and soil saturation, heavy monsoon rainfall, reduced soil cohesion, weak geological structure and steep slope increase landslide risk. Seismic activity, earthquakes compromise slope integrity, raising landslide probability, regional impact, access route block, home abandoned, and daily activity disrupted. Next is geological context. Location is at Lesser Himalayas. Susceptibility, prism thrusting and limestone deposition, weakened slope. Recommendation: conduct terrain analysis for slope stability assessment, improve soil compaction understanding via sand replacement test to develop mitigation strategies, focus on physics of soil under varying saturation level for infrastructure durability and risk reduction.
Hi, Assalamualaikum. So I will continue our present for the application. Soil compaction affects slope stability, with polycompact soil being more prone to failure during rain or earthquake. The sand replacement method is used to assess soil density and compaction. It's also helping engineer to identify which one is the weak area. In Havilian, Weakly compact soils increase the permeability and landslide risk, especially after heavy rain or seismic events. Engineer can use this method to improve soil strength and also reduce landslide risk by reinforcing vulnerable zones. So I will continue to the application, and this is about the sand replacement method and its application to landslide. So what is the sand replacement method? The sand replacement method is a technique that we use to determine the dry density of soil by removing a small sample from test site and then we filling it the resulting hole with sand of known density. This method helps to evaluate the compaction level of the soil, which is very crucial in assessing soil stability in landslide-prone area. In landslide-prone regions like Heavilian, soil compaction play a critical role in slope stability. Weakly compact or polyconsolidated soils are more susceptible to failure during rainfall or seismic events. These soils have a reduced ability to resist force from water infiltration or ground shaking, or increasing the risk of landslides. So, in the case of the heavy rain regions, the soil density was found to be 1,500 kilogram per meter cube, which indicate weak compaction. These weakly compact soils, combined with other environmental triggers such as heavy downpours and seismic shock, and it could have contributed to the occurrence of landslide. Therefore, evaluating soil compaction through the sand replacement method can provide valuable insight into how various factors contribute to the formation of landslide, especially in regions vulnerable to such natural disaster.
Hi, my name is Muhammad Faris Hakim. So, on this slide, we'll discuss the detailed steps on the sand replacement method used to measure soil density and stress conditions. Let's break it down step by step. First, soil sample excavation. First, we excavate the soil, typically 0.1 until 0.2 meter cube per block, using an auger or a soil sampler. It's crucial to choose excavation sites that represent the target area accurately. For landslide-prone regions, we need to test multiple zones along slopes to ensure precise results. This process is supported by research such as Shah et al. 2015. Second, estimating soil volume. Next, we determine the cavity's volume by filling it with dry sand of no weight and measuring it. To maintain accuracy, only uncontaminated uniform sand is used. This step aligns with guideline from Lee Kim 2013. Third, filling the hole with sand. After excavation, we fill the hole gradually with sand using a pouring cylinder. Care must be taken to avoid wet sand as it can alter density. The sand's density and consistency are recorded to provide reliable data as outlined by Smith and Jones 2014. Number 4, weighing sand. Finally, we weigh the sand before and after pouring using a balance scale. This ensures precise measurements of soil density and stress conditions adhering to ASTM D 1556 2015. This method is a systematic and reliable approach, ensuring the soil's properties are accurately determined for geotechnical analysis. After that, on this slide, we focus on the calculation of in situ soil density using the sand replacement method. Here's how the process works. Okay, first, formula explanation. The formula for calculating in situ soil density is P equal to MS over Vs, where P, not P, the symbol like that, represents the in situ density of the soil in unit kg per meter cube. MS is the mass of the sand used to fill the hole in unit kg. Vs is the volume of the hole meter cube. This calculation is essential for assessing the soil's compaction level and understanding potential landslide risk as noted by Shah et al. 2015. Second, testing in multiple locations. To get accurate results, tests are performed across different locations. Variations in soil's compaction can occur due to rainfall or seismic activity. This is particularly important in landslide-prone areas as emphasized by Lee and Kim 2013. Third, applicable soil types. This method works for both granular soils like sand and cohesive soils like silt and clay. To ensure accuracy, we use dry uniform sand following the standard of ASTM D1556-2015. By following this procedure, we can derive reliable data for geotechnical evaluations and enhance infrastructure stability in challenging terrains.
So in this slide, I will talk about the procedure and also the importance of the Havilian landslide study. The sand replacement method of the Havilian landslide study followed ASTM D1556 standards. The ground was level and the sand cone apparatus with a funnel was used. A metal plate with a hole was placed to define the cavity size. The hole was dug and the soil was collected and weighed. After excavation, the cavity was filled with calibrated sand, flowing freely through the funnel and it matched the ground surface level. The weight of the sand was recorded and the volume was calculated using the sand known density. In situ soil was determined by dividing the weight of the excavated soil by the cavity's volume. The method is easy to use with a few technical requirements, making it suitable for area with limited equipment. It simplify its simplicity ensures reliable product, even in remote location like the Pacific Island or polluted control programs. The sand replacement method offers several advantages, such as providing consistent result regardless of field condition. Unlike laboratory tests, this method directly measures the soil bulk density in its undisturbed state, offering a more accurate reflection of the soil properties in real-world conditions. The sand replacement method is helpful for projects like the Havilian landslide study, where understanding real on-site stresses is key to analyzing the failure mechanism. It helps engineers to see how soil properties work in natural conditions, which is more reliable than lab tests. The method was applied at three locations to capture the soil density variability along the landslide failure surface. This measurement offers insight into the compaction and heterogeneity of the material. The results along other tests were essential for analyzing the landslide behavior, identifying weak zones, and designing mitigation measure to prevent future failures in similar area.
Assalamualaikum and hello to everyone. My name is Muhammad Haikal Faiz bin Misman. My number main-entry is CF240127. Thanks to our group members for present just now. So today I want to present to all of you is discussion. The heavily landslide demonstrate that the intricate interplay of geological, environmental and human factors in triggering catastrophic slope failures. Key observation reveal that the underlying geology, characterized by weathered limestone and dolomite, played a critical role in the instability of the slope. This material, prone to erosion and compaction, set the stage for vulnerability when combined with external stresses such as seismic activity and heavy rainfall. The earthquake on October 26, 2015 created tension cracks in the slope which allowed water infiltration during subsequent rainfall. This infiltration increased pore water pressure and reduced the shear strength of the soil, culminating in the landslide. The sand replacement method findings confirm that the low soil compaction in the affected area significantly contributed to the event, highlighting the importance of in situ soil density as critical factor in slope stability. The role of human activities, including inadequate geotechnical assessment and slope modification, cannot be overlooked. A lack of proper drainage system and slope reinforcement measures exacerbated the condition. This underscores the need for improved infrastructure planning and geotechnical practice in landslide-prone areas. Furthermore, the study emphasizes the importance of integrating multidisciplinary approach in landslide risk management. While geotechnical assessments are vital, incorporating advanced technologies like remote sensing and geographic information system (GIS) can improve the detection of vulnerable zones and enhance early warning system. Coupled with public awareness and community engagement, this measure can significantly mitigate the impact of future landslide. Okay, next, the last one is the conclusion. The heavily landslide serve as a stark reminder of the devastating consequence of geotechnical failures in regions prone to seismic activity and heavy rainfall. This study highlights the critical role of soil compaction and poor water pressure in slope stability. The combination of poorly compacted soil, geological weakness, and external stresses such as earthquake and rainfall created a perfect storm for the landslide. The application of the sand replacement method provided essential insights into the in-situ soil density, enabling a better understanding of the factors contributing to the landslide. Future efforts should focus on enhancing slope stability through improved geotechnical assessment, reinforcement techniques, and effective water management strategies. By addressing these factors, it is possible to reduce the risk of landslide and safeguard life, infrastructure, and environment in vulnerable regions. In addition, the findings highlight the need for policies and regulation mandating thorough geological and geotechnical studies for construction in sensitive areas. Long-term monitoring of slopes coupled with investment in robust infrastructure can create resilience against natural hazards. It is imperative that government agencies, engineers, and local communities collaborate to adopt proactive measures that prioritize safety and sustainable development in landslide-prone areas. Okay, that's all from Group 3. Thank you for watching.